Okay, so I think last time around, I put you through lots of derivations, and we didn't do any problems. So let's do problems. We understand the derivations through actual examples. So let me recall the different things we did. One was, I think it is the windows left open because it's very hot inside. The air conditioning, it's 77 degrees inside. So you may want to leave it open so we can breathe. Is the noise distracting? But if it does, we can, yeah. So if you have a dipole, which will be represented by an arrow, we're visualizing this as plus q and minus q, okay? Separated by a distance, the vector itself is d. Then if the electric field in this region is uniform, we know that there's no net force on the dipole because the force on the positive charge cancels the force on the negative charge. But if it is not uniform, there is p dot gradient as an operator acting on the vector E, and the vector E is to be, or this quantity has to be evaluated where the dipole is located. Okay, and then even if the electric field is uniform, there's still a torque acting on it, and that internal torque is given by P cross E, but you may be computing your torque about some origin, and if I draw a straight line, it doesn't look as good, so let me you may be calculating torque at this point, okay, where torque is computed about a point, okay? The first term that we calculated was the torque about this point. But then you may be located, as I mentioned, in a different point, and let me draw this vector. If I call this R, then there's a correction, which is R cross F. And what F do we use? Precisely the force on the dipole. So a simple problem that Griffiths puts up shows all the complexities of the situation. So I'm going to do, it's a combined 4.5 and I think 4.29. I'm doing it simultaneously. I'll describe the problems as we do it.
Is it an example?
Yes, it's no, it's a homework problem, but I'm doing it nonetheless. Okay. To do this problem, I need the following expressions for the electric. I'm not even telling you what the electric field is. So, I mean, sorry, not at the moment telling you what the problem is, but suppose you have a dipole, okay, that is perfectly aligned to the z-axis. In the previous chapter, we computed ER, E theta, and E phi. Because of spherical symmetry or axial symmetry, the electric field along the phi direction is 0. Both of these had a 1 over 4 pi epsilon naught, I think, or I don't know, I can't recall if it is 2 pi epsilon naught. And the electric field fell off as 1 over r cubed. And I think this was P, the magnitude. Please confirm P cosine theta and over here it was 2p sine theta. Please look.
I think the cosine theta had the 2.
Okay, but either way, please look. Go back to your textbook, locate it, or notes. Because we'll be using this fact. You are correct. Cosine had the 2. Yeah?
Quick question about just dipoles.
Yeah.
Because we have this P symbolizing the dipole, and P includes Q and D.
Correct.
We can have two of the same, like we don't see the fact that the charges might be the same as long as the distance compensates for them, and the distance might be different as long as the charges. Right?
So, yeah, so the physical dipole,
Like the physical dipole might be
Yeah.
different, but
Yeah.
the force and
you can literally think of it as a vector where charges are separate, but if this is actually true, this is only an approximation. In the limit, as the distance goes to 0 and q times d remains finite, then this is exact. But it is much more easier for us to work with the idea that this is an approximation. This is to 1 over r cubed. That's good enough. Because beyond that, the numbers are small enough. So now let me describe the problem. There are two dipoles. Okay. There is a dipole here, and it's called P. And the origin, this point right here, where the center of the dipole is, I'm just going to call it A. Okay, that's where the dipole is actually located. And then there's a second dipole. And this guy, I'm going to call that location B. And the dipole, I cannot just have P, there's P1 and P2. So I'll call this P2, and I think Griffiths does it. No? Okay? Oh, no. Yeah? Good, James? First, I'll compute the torque on P1 due to P2 about the point A. Because I'm computing the torque on this guy, about this point, I don't have this term. So all I need is P, which I have, it's P1, cross E. Well, what E? E due to this guy on this charge.
The reason we don't need that second term is
because I'm computing the torque on P1 about P1.
Yeah.
So I need to get the electric field here. So this is a subsection. Now this problem is this dipole is aligned along the z-axis. Here it's aligned along the. Let me call this way, y and z. Y along the y-axis. No matter. It translates to this if the angle can be chosen so that theta is pi over 2. Correct? Because if this is a z-axis, then this point would be pi over, sorry, not pi over 2, pi. You nodded your head to both. Which one is it? Pi, the entire pi. Okay? So here, theta in this set of equations equals pi, and cosine of pi is -1, sine of pi is 0, so the electric field is in the radial direction. So, radial meaning that direction. Correct? Now pretend as if this is temporarily my z-axis. When I say radial, I mean, if z is that way, this is radially pointing downward. Yeah? So, watch this. 4 pi epsilon naught 1 over r cubed. This distance is r. We'll continue to use r. Two times the magnitude P2 cosine of pi. You should tell me. Oh, you're still here.
Yeah, I got stuck in the elevator for like the past 10 minutes.
For the past 10 minutes?
Yes, it didn't move. And it didn't open, and we rang the little alarm thingy, and no
Yeah.
one picked up. Like, it was like, it was me and another, yes, yes.
I mean, sometimes you get it and then you
We
just take
tried,
it,
no,
right?
we tried to open it, we tried to push the button, nothing worked. We was stuck in there.
I'm glad to see you got out of the cage. I want you to be happy with all the terms and realize that this is the electric field. Radially outward is negative y hat. Look, this is the term that's 0. Sine of pi is 0. So it's radially outward, which if this is the origin, this is radially outward. And that corresponds to minus y hat. Yeah? Everyone good?
We go over that cosine, the pi term, the pi angle.
Oh, so if this is my z-axis, angle is measured from here. So this is pi.
To line up with that radial.
Yeah. To where, if you start from here, and that's the z-axis, where is this located? I'll erase this. That's literally like asking, where is this?
Okay, yeah, that's it.
So that is cosine of
Yeah.
pi, and it's ER, which means it's a radially outward direction. That's this, and that corresponds to that. So, yeah, you have to learn to bend and stretch while you do physics. Look at all sorts of angles. Okay, so let's compute the torque. It is P1 z hat cross 1 over 4 pi epsilon naught 2p over r cubed y hat. Nope, this cannot be p, it's P2. P2, 2 P1, P2 minus 4 pi epsilon naught 1 over r cubed x hat. Y cross z is x, z cross y is minus x.
I just want to add something. For that part, E theta is equal to 0 because pi is equal to, theta is equal to pi, right? Just to,
I'm sorry, correct. E theta is 0 because theta equals pi.
yeah.
Yep. Now let's compute torque on P2 about P1. Torque on P2 due to P1 about its own origin. Don't worry, I will not keep you from the pleasure of changing origins either. But let's do this very quickly. So I'm computing torque about this point on this guy. So I need the electric field here. That's all that matters. In this case, theta equals what? The electric field at this point due to this dipole. So tell me now, what is theta? Pi over 2. And so it is E theta. Yeah? Now E theta points which way? Downward. Theta hat. So it is, the electric field here is 1 over 4 pi epsilon naught 1 over r cubed P1 sine theta is 1 and the direction, which is always the crazy thing to remember. Then the torque is equal to P2 cross E, which is P2, whoa, not y hat, minus z hat. P2 y hat cross 1 over 4 pi epsilon naught 1 over r cubed P1 minus z hat, and that's equal to what? Minus 2, no 2, P1, P2, 4 pi epsilon naught, 1 over, not R3, but R cubed. Y cross Z is X hat, so minus Is that true?
Because you already pulled out that first negative.
Yeah, I pulled out this.
And then just leave it black out.
So let's make sure P2 is Y hat, and the electric field is downward, it's minus Z hat. Yeah. Yeah? Now you find that these torques don't cancel each other out. They don't have to because I computed them about different origins. Otherwise you would think, you know, the Newton's third law, what's good for the goose is good for the gander. That's got to happen, right? It's got to cancel each other out. But it doesn't. No surprise. This is torque about A. This is torque about B. So then, obviously, I want to use this calculation, and I don't know where I'm going to do this, which means I'll have to do a little bit of editing today.
Talk about some
Torque on P2 due to P1 about A. Previously, we computed it about B, but we want to compare torques about the same point. So obviously, I need force. So I need force on P2 due to P1. So force is equal to P2 dot gradient acting on E due to P1. Are we good? Okay, so let's make the dot gradient easier. I'm going to make it as Y. Yeah, I just skipped a step. That's why. Because yeah? That's why. That is equal to P2 dy. We just computed the torque on P1, torque on P2. Yeah. Isn't this the electric field? You know, one thing I always hated was instructors doing crazy things without explanation. What do you think that explanation is? Yeah, it's I'm taking derivative in the y direction, right? So r is just the y coordinate. And then once we take the derivative, we can change it back to r. So that is minus P1, P2, 4 pi epsilon naught, 3 y to the 4th z hat. Ashik, you're not happy.
Remind me how was the negative z hat again?
So it's the electric field at this point due to this guy.
Mm-hmm.
So I'm putting theta equals pi over 2. So when I put theta equals pi over 2, this goes away. It's this term. But that's E theta.
Right.
At this location, which way is E theta pointing? Down the longitude.
Wait,
Spherical coordinate system. This is my z. This is how theta.
yeah.
Yeah. So
Okay.
that is
Oh,
1
okay.
minus. Yeah. Therefore, R cross F again, R times, in this case, it is y hat cross F P1 P2 over 4 pi epsilon naught 3 times, now watch this, again, R to the 4th Z hat. And that is 3 P1 P2 over 4 pi epsilon naught 1 over R cubed X hat. Huh? Yep, exactly. So then the torque becomes what? Minus P1 P2 over 4 pi epsilon naught 1 over R cubed X hat. This is the old P cross E torque. Now plus the R cross F compare it to both about point A, and we find that torque on P2 due to P1 about A is equal and opposite to the torque on P1 due to P2 about A, about the same origin. So problem 4.7, the goal is to show the interaction potential energy of a dipole with an electric field. Okay. So I'm just going to set up a little bit of notation. This is, of course, the vector d over 2, and this is the vector minus d over 2. There's a charge minus q, there's a charge plus q, and I'm placing my origin y, z, and x-axis. This is not the x-axis, but this is in the zy plane. It doesn't matter. This is the direction of the dipole. In fact, these axes do not really matter, so I'm not going to label it. The potential energy is easy. Remember, the dipole is not seeing itself. That means this charge is not interacting with that charge and vice versa. Well, it is, but we're ignoring that. We're talking about the external interaction energy. Okay, well, simple enough. Q times the potential at d over 2 minus q times the potential at minus d over 2. This can be written as minus q times delta V Q times delta V, which is nothing more than minus Q integral of E dot dl from minus d over 2 to d over 2. Correct? Because that's what the potential is defined to be. Okay, like I said, this is the correct answer, but we're not looking for the correct answer. We want it to be a dipole. We want to only calculate this to order D. Secondly, again, I want to reiterate, we're not talking about the dipole, the plus and minus charges interacting with itself. This potential is due only to an external electric field. You know, some of the molecular forces are requiring the dipole to stay like a dipole. A water molecule just has a dipole moment. Well, it is curious to see why that is stable, but that's a different question. Our question is, now a water molecule is interacting with the electric field, external electric field. What is that interaction energy? That is why I didn't include any dipole, plus charge, minus charge interaction at all. All we are left to do is approximate this to first order in D. So I will write dl to be equal to some magnitude ds. In this direction of D, it's a unit vector in this direction. I just can't think of a better term. Yeah? And then electric field at any point where this corresponds to S equals 0, huh? Well, you know this. I'm going to Taylor expand, so I can put this as approximately E0 plus that at any other point S, my Taylor expansion, S d hat dot gradient E evaluated at 0. Yeah? And I stick this back in. So U is going to be equal to negative Q. Let me do my favorite integral first. Plus the integral I'm not going to do. But I have to explain why I want to do that. Plus, I'm going to factor the negative Q out. Integral. This is a constant. Well, I can even make that very clear. This is d hat, sorry. This follows my calculation from yesterday. Make sure you understand where all the terms are coming from and why I pulled out certain terms out of the integral, why I did it.
If you pulled
because it is evaluated only at the origin. So it doesn't change with S anymore.
So then why didn't you pull it out of the first one?
Oh, right, I get, oh, sorry. Yeah. But, listen. Yeah? This is what? S squared over 2, D squared. And Q times D is so this result is often used in quantum mechanics. We won't particularly use it, I don't think, for the rest of the semester. But next year, when your quantum instructor tells you, that's the interaction energy of a dipole, you'll recall back.
So that term, d hat, ds.
Yeah, see, it is this dot dl. I wrote it in altogether of a messy way. This is dl.
Yes. And then,
This s, I brought it over here.
right,
Then there's a dot product, so it's this, which is a vector, dot the dl, so that d hat.
On final line, so we have
Yeah.
E dot D vector, would that be E dot D hat?
No, oh, I skipped steps again because I know the answer. When I integrate ds from minus d over to d over 2, I'm going to get d.
Oh.
But good, as such, it's a good question.
so how was SDL, how did that term go to 0 again?
Because when I integrate s ds minus d over 2 to d over 2, I would get s squared over 2 from minus d over 2, d over 2, which is what? 2 times, there's this 1/2, then I have d squared over 4. Isn't that d squared over 4? I don't know if it's d squared over 4 or, yeah, it sounds like it should be d squared over 4.
But I thought you called d hat dot, well, d hat ds dl. Isn't that what you were doing over there?
No, I call dl
Uh-huh.
ds times d hat.
Okay.
So this is my dl. And s, I'm importing from this term.
Right.
Right. So I can even pull this out of the integral.
Mm-hmm.
See, I can even do this because these are constant vectors. So it is just s ds. And the point here is it is d squared over 2. Well, none of these equations are accurate to that level. We want it to be accurate to first order in D. That is what dipole approximation means.
Oh. I was going to ask you, where did the second d hat come from? I see where it came from.
Yeah. Because I'm evaluating this at any point SD hat.
Yeah. Yeah. There's already a D hat in there,
Yeah,
and then
so
the second one.
I guess I could even make that clear. Good, good. I like all of those questions. Because at any point along the dipole, it is some unit, some distance s away, but it's in the direction of d hat. I think we have earned our class medal today. Good problems.